It's a bit of an intro, and we do have quite a bit of content to go through. Our topics are going through a history of deployment and microservices really quickly, and then we'll get into the meat and potatoes of container orchestration. So without further ado, in the early days of computing, we deployed our applications directly on these physical machines. And at the time, it was cool. It provided strong isolation for each application, pretty predictable performance. But issues such as hardware costs, a lack of flexibility, led to the development of a much more efficient and cost-effective solution, which is virtual machines. Now, VMs are created on a single physical hardware, a single physical server through a hypervisor, which acts as a sort of virtualization layer. And it also has its own guest operating system, and it runs applications within a separate VM. So VMs are cool because they have the same strong isolation that physical machines have. They also are more flexible, so that was pretty much the benefit, among other things. Unfortunately, they're pretty heavy. As you can see, each VM has its whole own guest operating system. And so due to this and their virtual hardware components, it does take up quite a bit of resources. Luckily, we are no longer in the 90s, so we have containers. Containers are basically, I don't know, I guess if you ever ordered like a desk from IKEA, you're probably expecting like it to come with all the bells and whistles, right? Like it should come with every nail, nothing should be missing. So I can build up my desk and it'll be perfect. So whether you're in California or Massachusetts, they're gonna ship me my desk and it's gonna come with all the parts. That's basically what a container is. They're like these packages that just hold everything your application needs to run consistently across different environments. These containers operate on top of a shared operating system. And unlike the VMs, which have separate guest OSs, we also have a container engine that we need for the containers to actually run. So for this, it could be something like Docker that just manages the creation and deployment of the containers. So containers are pretty cool. It has a lot of benefits. They're lightweight, which means faster spin up time than VMs, and also uses a lot fewer resources than VMs. So maybe you wake up one day, you're like, hey, I want to containerize some of my applications. And so as the use of containers grew, it naturally paved the way for a new architectural approach, which is microservices. And I know we're all familiar with monolithic applications where you have one big application, like business logic, and then like a database, like these like just big chunks. But microservices breaks down applications to smaller independent services, and this brings a lot of cool advantages. The main one, which is that it pairs exceptionally well with containers. So each microservice can be containerized, further enhancing your deployment and scalability. So you realize, hey, okay, cool, microservice architecture is cool. It meets the needs of my application. I can containerize some or most of my services. And then you suddenly realize that, the more services I have, I think networking is starting to get incredibly complex, and connecting my different containerized services can be incredibly difficult. So you start asking yourself, well, what if one of my containers dies, or maybe like a service stops running, or like, what do I do if my services are failing to communicate? How do I scale my containers when needed? All these moving parts, like how do I manage my containers when my application gets to be on a really large scale? And with that, I will introduce you to our first tool, a container orchestration tool. For this purpose, I will be introducing you to Kubernetes. And Kubernetes, as I said, is a container orchestration tool that was developed by Google as an open source inspired by their internal cluster management tool, which was called Borg. So I want you to take a quick look at this model because it's going to come up again, and it's also the model that Kubernetes architecture follows. We have an orchestrator, it's pointing to different worker nodes, and these nodes are holding or hosting containers. So just keep that in mind or take note of it. Now this is our Kubernetes architecture diagram. This, in the context of your application, it serves as a framework to simplify the deployment, the scaling, and the management of your containerized services. It's pretty much the backbone of your application. Our master node and our worker node here are in what we call a Kubernetes cluster, and then we have you as a developer. These are the three parts that I'm going to discuss quite briefly, so do not worry. We're going to go through each one, starting with the worker nodes. Each node represents a virtual or physical server. Within each node, we have a pod that encapsulates your application containers and any resources that are required to run them. We also have a container runtime engine. In this case, it's Docker. Every worker node comes with one in order to run the containers. We have a kubelet, just make sure the containers work as they should, and a kube proxy that maintains network connections. The next very important component is the control plane. The control plane is kind of like the brain of the operation, and there's four parts here that I want to go through. I'm probably going to talk a lot, but I'll put the main notes on the actual slide. So the API server, all external communications pass through the API server. You receive REST requests to your pods, controllers, and any service modifications comes through this API server. Your scheduler keeps an eye on the requests from your API server. And if there's one thing you take away, just know that it allocates pods to nodes. That is what it does. I think that's the most important thing to remember. And then next we have up here, we have a key value store, the etcd. This is what holds our desired state. It's a database that stores the backup of our entire cluster data. You can just think of this key value store as the single source of truth for all of our cluster data. We want our cluster to have the desired state at all times. And how do we do that? We go to the controller manager, which makes sure our desired state is maintained. It regulates tasks and maintains the clustered state. If we change our desired state and we say, hey, instead of 5 pod instances, I want 10, the controller will look at the desired state. It will then look at the cluster and it will decide, hey, we're not matching. I need to spin up 5 more instances so that I match our desired state. And that's basically what the controller does. It has a lot of other, miniature separate parts into it too. I have extra resources because I don't have time to get into all that, but that's basically what the controller does. I also do keep mentioning desired state. That is because you, as a developer, will have to make your deployment file. This is what contains and manages the desired state for your application. You're able to specify parameters, including the number of pod instances or replicas, as we see here, that you want to run, or the version of your application, how to update the application, all that information is handled here. So as I had mentioned before, if you want to specify instead of 3 replicas, maybe you want 5, this is the place to do it. So yeah, I've showed you all these components. You're probably like, Blessing, that's cool. So what does Kubernetes actually do? It just maintains the desired state of your application. If we were to put it into one sentence. So if you remember all those questions I had where like our containers are dying, like, oh, what if one of my containers dies? Or like, what if a server stopped running or my services are failing to communicate? Yeah, Kubernetes will just handle all of that for you. The controller manager, as we just went through, is constantly comparing the desired state with the actual state of the cluster and making changes as needed. So if our desired state lowers from 10 pod instances down to say 2, the controller will terminate pods, will terminate 8 of your pods to match that new desired state. And we can also scale up and down to handle traffic accordingly, however you want to. So you don't need to run around managing each one of your containers and worrying, because that's essentially what Kubernetes was built to do. In addition, you can just hop on the bandwagon because there's a lot of companies already using this technology. Google, because they created it. We have Spotify, Capital One, Adidas, New York Times, Pinterest, Airbnb, even Tinder has shifted in the last decade to not only containerizing their applications, but orchestrating these containers with the help of Kubernetes. So I know she must be thinking, blessing, that's cool. It seems like a great tool. When are you going to drop the bomb? What are the downsides? Well, because Google is not sponsoring me, I will tell you the downsides of Kubernetes, which is that it is incredibly complex. It has a pretty steep learning curve, can be pretty complex to manage. Even what we went through, I went through in like a couple of minutes, but there's still so much deeper we can get into it. Configuring the cluster, understanding the different components, monitoring and troubleshooting, yeah, so it's a lot. It is a complex tool, but to be fair, it is meant for complex applications. That's why Google uses it. And it's probably not for your run-of-the-mill to-do list app. So I would say that's the main downside. And if you can overcome these initial challenges, there's a host of benefits. I think the pros outweigh the cons. Kubernetes does follow a certain architecture. I made this a bit easier to look at, but it should match what I showed you earlier. We have our control plane here, which is essentially the master of the operation and connected to worker nodes that hold our pods, that hold our containers. And well, the reality is, and I could have told you this in the beginning, but I think this is a lot more fitting, most container orchestration tools actually follow this exact format. Well, not all of them, but quite a bit. The master worker architecture model is essentially just a central manager that we have here that connects to multiple nodes that host containers. The title of this presentation was actually orchestration tools, so I can't just talk about Kubernetes. What about Docker, Swarm? This looks like a little familiar, no? Docker Swarm, we have a manager here that's handling the orchestration and is communicating with the Swarm agents running on each node to manage the container deployments. And it pretty much does match our master worker model. There are obviously key differences between Docker Swarm and Kubernetes. For the most part, I think Docker Swarm is a lot more user-friendly. It's less complex than Kubernetes and probably a lot easier to onboard. But architecturally, they are essentially the same picture. Overall, this talk is supposed to be a lot more than just like going through what Kubernetes is. And I want you to leave knowing that there is like an underlying model that makes what it does possible. So now you can rest easy, knowing that whether you're trying to onboard Kubernetes, Docker Swarm, or some other container orchestration tool that also uses this model, something like OpenShift or Mesos or Amazon Elastic Kubernetes Service, whether you're onboarding any one of these tools, you have a solid foundation on getting started. And that is what I hope you're able to take away from this tech talk. Here are my works cited page if you're interested in more information. I did gloss through a couple stuff pretty quickly. You can also contact me on my LinkedIn, email. You can check me out on GitHub. I also do pigeon posts. You'll have to message my pigeon for that, and his email is down there as well. Thank you all so much for coming to my tech talk.